These are the spiders in your yard.
Hello YouTube! I'm really excited to cover this species because they're particularly beautiful and impressive and fascinating to me. I don't know if there were more of them out there this year, but it got to a point where coworkers and friends would come up to me with their phones out, clearly searching for a photo to show me, and I'd had the conversation so many times by then that I knew I was about to see Argiope aurantia, the yellow garden spider. This is a fairly large orb-weaving species native to North America, very recognizable from its distinct markings and often quite intimidating to people who are unfamiliar with it, and particularly intriguing as it makes this distinctive pattern in its web. Now naturally, I'm going to address the usual questions people have with any spider, like how to identify it, where you would find it, how it hunts, and whether it's dangerous. But the yellow garden spider presents other riddles as well. Why is it so brightly colored? And what on earth is that zigzag for? I'll get into all of that with a close look at what we know, and perhaps more notably, what we don't know about these spiders. Because despite having studied them for like 150 years, there's still a lot of mystery. These spiders have close relatives pretty much all over the world, so if you haven't encountered exactly this species, you most likely have encountered one of its cousins. And they're all fairly similar, so most of what I say here will apply to them as well. A quick word of thanks to those who helped make this video possible. Catherine Scott, Sean McCann, Courtney Christie, Nancy Miorelli, Giselle, and my wife for her suggestions which vastly improved this script. Thank you all. And now, into it. As spiders go, this species is honestly pretty easy to spot, or at least the females are, because they're fairly big, with body lengths ranging from 19 to 28 millimeters, 3/4 of an inch to a bit over an inch, and a leg span quite a bit beyond that. Now, not all of you are from the same part of the world, so I'll use a variety of things for scale here. Here's one next to a Canadian quarter. Here she is next to an American quarter. Here's the same spider next to a 3rd century Roman Antoninianus. And if you're not familiar with any of those coins, here she is next to a standard Lego minifigure. I would say this one was a fairly average size for a mature adult female, and they may get a little bigger or a little smaller, but this is a good general idea. This abdomen, or opisthosoma, is the most prominent part of the spider, and this pattern here is distinctive to the species. 2 to 4 pairs of yellow markings running down the middle, with broken yellow patterning along the sides, and these 2 shoulders near the front. The prosoma, or cephalothorax, is interesting up close because it's actually covered in silver hairs. And that's where this spider gets its name. Argiope in Greek means silver-faced, and aurantia means gilded or covered with a thin layer of gold, referring to the yellow gold patterns on the abdomen. Now, I've heard this pronounced a number of different ways, like Argiope and Argiope. You could argue that any of these are correct. I'm going with Argiope. This is basically the GIF-GIF debate. No one really cares except for the people who do. However, it is definitely not Argiope. That is wrong, like the most wrongest way to say that. Moving on to other details, legs 2, 3, and 4 have yellowish light-colored femurs, with the rest of the leg going to black or sometimes banded, while the first pair of legs has dark femurs usually. If we're looking at the belly side, we'll see this short yellow stripe right down the sternum, and these 2 yellow zigzaggy lines down either side of the abdomen, ending at the clump of spinnerets. Now that's the female. This species, and actually the whole genus this species belongs to, Argiope, displays dramatic sexual dimorphism, which is when the male and female of a species look quite different from each other. In this case, specifically sexual size dimorphism, to a degree rarely seen in the natural world. Much like goldenrod crab spiders, which I covered in my last video, male yellow garden spiders are much, much smaller than the females, reaching only 5 to 8 millimeters of body length, about 1/4 the size, making them much more difficult to notice, and in fact, I've never actually found one myself. They do have a similar pattern on the abdomen, but it's far less brilliantly colored, and the abdomen itself is much smaller relative to the rest of the spider. They also have a dark prosoma with bits of silver, not the solid silvery sheen of the females. And if you didn't know what to look for, you might not recognize them as the same species of spider at all. This dimorphism occurs across the whole Argiope genus. Going back to the females though, why do these spiders have such bright coloration? First, keep in mind that in spiders, the male's job is generally just to live long enough and move quickly enough to get to a female before all the other males do, and mate. In most cases, they die shortly after mating. In some cases, believe it or not, during. There are worse ways to go, I guess. But the female's job is pretty much to gain as much weight as possible. What a life. To produce as many eggs as possible. Thus, she's better adapted for catching lots of prey, and it's possible that this bright patterning is all for that purpose. There were two leading theories about this. One, that the color pattern broke up the outline of the spider, making it less visible to insects against the chaotic background. And two, that the yellow markings themselves actually attracted insect prey, mimicking the colors of food sources such as flowers. To figure out which one it was, Alex Bush, Douglas Yu, and Marie Herberstein bothered some spiders in England back in 2006. They found a patch that had a lot of Argiope bruennicae, wasp spiders, very similar to our yellow garden spider, and applied 3 different treatments to them. One group, the luckiest one, was left entirely alone, so they functioned as the control group, and probably had no idea they were part of an experiment. Another group had leaves hung in front of them, obscuring them from view. The third group had their yellow markings blacked out with a xylene-free marker, rendering the entire abdomen plain black. The logic was this: if the markings functioned as camouflage, then the unmarked spiders and the spiders hidden by the leaf should both catch more prey than the blacked out spiders whose camouflage had been ruined by the ink. But if the markings attracted prey, then both the spiders hidden by the leaf and the spiders with blacked out markings would catch less prey than the unmarked spiders, who still remained blissfully unaware of what was going on. They measured prey capture for about 3 weeks, and it turned out that the naturally colored spiders captured on average twice as many prey than both of the other 2 groups, and 3 times as many orthopterans, insects belonging to the order that includes grasshoppers and crickets. So the markings appear to actually be attracting prey. Where in the world will you find the yellow garden spider? This one is, in fact, native to North America, and is found pretty much nowhere else. They occur as far south as Guatemala, and in the north, I don't know if they've got something against Western Canada, but they seem to abruptly stop occurring right at the 49th parallel. Those parts of eastern Canada that dip below 49, like southern Ontario, Quebec, and the Maritimes, will see them though. Fun fact, did you know that the southernmost part of Canada is at the same latitude as Crescent City, California? Now you do. They also seem to avoid the drier parts of the US, Arizona, Nevada, Utah, Idaho, but they're present in most of the mainland United States. Now, you might live outside of that area and be thinking, but Travis, I'm sure I've seen this spider here in Germany, or wherever else you might be. The Argiope genus to which this species belongs has representatives all over the world. The various different species can look very similar, but have some patterning differences. In North America, the relative you're most likely to run into is Argiope trifasciata, the banded garden spider, and it also occurs in South America, Southern Africa, Australia, and parts of Southern Europe. Argiope bruennicae, the wasp spider, looks nearly identical and can be found in Central and Northern Europe and through Asia. In the southernmost parts of the US, as well as in Central and South America, you might encounter Argiope argentata, the silver garden spider, and its very cool spiky butt. In total, there are currently 89 accepted species in this genus, spread around the globe, with the northern limit of their range being somewhere around Edmonton in North America and somewhere around Helsinki in Europe. But the yellow garden spider, Argiope aurantia here, is limited to North America only, and only from Guatemala up to about the 49th parallel. Within that range, what kind of places do they hang out in? First and most obviously, these are a kind of orb weaver, so you won't find them under a rock or hiding behind your siding. They'll be in a web. And they'll make those webs fairly close to the ground, around knee height, instead of rudely placing them right at face level, like many less considerate orb-weaving spiders do. I've found them in wild grasses next to roads, in the frames of low windows, and in low bushes in gardens, so they're not too picky. In 1970 and 1971, a study to determine the preferred habitat of these species was done by Frank Enders from the North Carolina Department of Mental Health, which is weird. He checked various habitats to see how many of these spiders he could find in each of them, and he also collected egg sacs, kept them over the winter, let them hatch in the spring, and released the spiderlings in different habitats at different life stages, then monitored them to see if they stuck around. He found that yellow garden spiders prefer edge habitats, where wide open areas meet dense vegetation, and that they will actively leave dense, heavily shaded environments in search of sunnier sites. And their webs are often fairly easy to spot because of this. This is called a stabilimentum, or sometimes a web decoration, and the webs of these spiders will usually have it. This is one of the most fascinating aspects of these spiders, and I'll discuss it further later on. But it's something you can look for if you're trying to find one of these spiders. I honestly can't blame people for being apprehensive around this spider if they don't know what it is. These aren't small spiders, first of all. Second, they weren't blessed with the adorable cartoony eyes of a jumping spider. Third, that coloration has a particular effect on us as humans, I think. This is the same color scheme we see in many bees and wasps, animals that can hurt us under certain circumstances. And the bright colors in animals often indicate powerful toxins or venom. And it turns out, some indigenous groups in southern Africa actually use Argiope australis as a poison on their hunting arrows. But they use the contents of the abdomen, not the actual venom. And the role and effect is still unclear. What's the reality of a bite from one of these then? Well, if we have a look at the fangs of this species, it's definitely big enough to bite a person and probably break the skin. It's unlikely to bite though, and these spiders are generally pretty shy. They'd rather run away than bite, and will only bite if they're stressed enough, which would probably require pinning them down and squeezing them. Now, this could happen accidentally, especially since these are common in gardens. You don't notice the web, the spider gets spooked and drops out onto the ground, then you move your knee and pinch it without noticing. Which seems to be exactly what happened in this case from 1968, where a 43-year-old woman was bitten while gardening, just above the knee, slapped the spot, and actually saw the spider. The initial effect was just immediate pain at the bite site, which is no surprise, but it worried her enough that she thought she should seek medical attention. This is where her choices become somewhat baffling, though. On her way to the hospital, she stopped at a service station, got herself some gasoline, and rubbed it on the bite. Of all the products she might have had at home, where the bite occurred, like soap and water presumably, gasoline is what she went with. At the hospital, she complained of a bit of pain in the groin, which might suggest a neurotoxin, but other than that, there was a red spot around the bite, a little more than an inch across, which itself may have had more to do with the gasoline than the venom. She was given an antihistamine and a topical corticosteroid. The pain went away, and she went home half an hour later. From the report, the attending physician felt that the mental state of the patient may have accentuated the physical effects of the spider bite. This idea and other questions relating to this case could not be pursued because the patient refused to cooperate. So, to me, the main takeaways from this are that if you manage to get bitten by one of these, first, don't freak out, and second,
don't put gasoline on wounds.
Now, this was literally the only confirmed bite case from this species that I could find in the literature. And usually when we have a species that commonly lives near people, but very few confirmed bite reports, that suggests that the venom is probably harmless. Because odds are that at least some bites are occurring. Statistically speaking, it's not common, but it happens. But the effects are so minor that nobody goes to the doctor about it, and thus there's nothing published. Research on the venom has found that it's not even all that potent to insects. While it can paralyze oriental cockroaches, it's not actually lethal to them. And chemical analysis found that its chemical makeup is simpler than most spider venoms. It's speculated that this might be a trade-off between the spider's two main weapon systems. Rather than invest proteins in the venom, these spiders invested in their silk. And this brings us to how these spiders hunt. Obviously, these are orb weavers, but remember how I said they tend to make their webs close to the ground? That may be because these spiders are specially, but not exclusively, adapted to hunt orthopterans, the family of insects that includes grasshoppers and crickets. And they use different tactics when attacking those than they do when attacking flying insects. A 1998 paper by Pasquet and Leborn found that when wasp spiders were presented with a fly, they bit it first, then wrapped it, then immediately carried it to the hub of the web to eat it. But when a grasshopper was placed in the web, they first wrapped it in silk, not making contact with it at all, then bit it. After that, they'd return to the hub, leaving the prey where it was, then come and get it after a little while, taking it back to the hub to eat it. This is exactly the behavior I saw from Madison here. Now, this girl was a rescue, having been unlucky enough to have made her web on the house of an acquaintance of mine who has very little tolerance for spiders in general. Madison was a brat initially, and would not put her web in the perfectly good frame I provided for her. The lengths I went to in order to get her to do so are documented on my Patreon page. But she eventually cooperated, and gave me the opportunity to observe her closely. When I fed her crickets, that is exactly what she would do. Rush out, wrap the cricket up, then bite, return to the hub like she wasn't interested at all, come back later, and drag the cricket back to the hub where she'd spend the next few hours eating it. This wrap attack is extremely effective and allows the spider to attack dangerous prey without ever having to actually touch it with her own body. It can also render some prey's defenses ineffective, as Thomas Eisner and Jeffrey Dean found in 1976. The bombardier beetle has an incredible chemical defense. When attacked, it emits a mix of chemicals from an aimable tip on the abdomen, which instantly react and reach the temperature of boiling water. When Eisner and Dean dropped these beetles into the webs of golden silk orb weavers, which look similar to yellow garden spiders but are in a different genus, they would rush to the beetle and immediately bite, causing the beetle to spray this stuff right in the spider's face. This consistently warded off the spider and the beetle escaped. But when they did this with yellow garden spiders, the spiders didn't bite immediately. They wrapped the beetle up, which didn't compel the beetle to use this defense. Then they bit it, and at that point the beetle would spew its boiling hot butt spray. But it would be A, unable to aim it, and it usually went harmlessly off to the side, and B, it was contained by the wrapping. Sometimes this would startle the spider a bit, but then she would just wrap it up some more, and eventually carry the beetle back to the hub and eat it. So the silk, not the venom, seems to be this spider's big gun, and that's where it invests more of its protein resources. Interestingly, spiders that make web decorations, including uloborids, which don't even have venom glands, all seem to use this wrap attack strategy rather than going for the bite right away. And orb weavers in general are able to quickly locate prey within the web based on the pattern of vibrations. If you're interested in exactly how, I discussed it in my video on the cross orb weaver, so go check that out. Yellow garden spiders may seem to focus on crickets and grasshoppers as prey, but they're not quite what you would call a specialist predator, as they're more than capable of taking other prey as well. A number of studies have been done in various parts of the United States to see what they're eating. In the cotton fields in Texas, one study found them eating a lot of aphids and leafhoppers, as well as bees and wasps. while in nearby grasslands they were preying mostly on grasshoppers. In Oklahoma, one yellow garden spider was observed eating a juvenile lizard. In one survey in Illinois, 40% of this spider's diet was lepidopterans, the order of insects made up of butterflies and moths. And when it comes to moths, we see a fascinating phenomenon. Yellow garden spiders are honeypot scammers. Hemiluca is a genus of moth that usually flies well above the vegetation canopy layer, much higher than where these spiders usually put their webs. And yet, males, and only males, of certain species within that genus have been found in Argiope webs. So in 2016, Andrew Warren and Paul Severns collected a bunch of these spiders, got them to make webs in mesh cages, then put the cages outside with empty cages nearby to see if the moths came to them. And sure enough, the males of certain species seemed very strongly attracted to these spiders themselves, while ignoring the empty cages. The spiders have apparently figured out how to mimic the pheromone that the female moths emit to attract males, making the male moths think that they're heading for a romantic encounter when what really awaits them is certain doom. So you've got these Argiope spiders essentially catfishing these poor moth dudes. But instead of emptying the moth's wallets, they're emptying out the moth. Interestingly, in some tests, the moths weren't attracted to the spiders on one day, but were the next. So either the moths are sometimes just not in the mood, or the spiders sometimes don't emit the chemical lure. But the fact that it seems to be very specific species within the Hemiluca genus, and in some species only certain populations, suggests that as the spiders have evolved this pheromone lure, the moths have evolved resistance to it, and some may have adapted to time their emergence so it doesn't coincide with when these spiders are active as adults in the late summer. This is called coevolution, when one species adapts in response to the adaptations of other species it interacts with. This is literally a snapshot of an evolutionary arms race in progress, with one species developing a hunting tool and the other developing a way to evade it. This spider's most mystifying adaptation, of which we still know neither the purpose nor evolutionary origin, is this, the stabilimentum. It was called that because it was originally thought to stabilize or strengthen the web, but further study found that the silk it's made from is woven too loosely to really do that. So this is now sometimes referred to as a web decoration, and web decorations from different spiders can take different forms. The trashline orb weaver makes one with the dead bodies of its prey. Within Argiope, though, the yellow garden spider makes two simple wedges, while Argiope argentata gets fancy and makes an X. Now generally a spider's web relies on being inconspicuous, so if a spider was going to do something that made the web a lot more visible, there must be a good reason for it. Scientists have known about this for a long time. Charles Darwin mentions it in an 1832 journal entry, so we're coming up on 200 years. And the famous naturalist Henry McCook, on observing this in 1889, wrote, "A future observer will doubtless find a simple explanation of the phenomenon." It's been 135 years since McCook made that prediction, and it seems we're not really much closer to figuring it out. And it's not for lack of trying. In April of this year, Andre Walter from Aarhus University in Denmark published a long paper reviewing the research that's been done so far. Much of the trouble is that when evaluated altogether, the findings of the past research are often conflicting, contradictory, unclear, and inconclusive. Walter writes in the conclusion of his paper, "Studying the existing literature to find answers is like opening a long-forgotten fishing bag. Everything is somehow there, but it seems impossible to disentangle the content." Well, I'm not one to run from complexity, and I suspect that you, inquisitive internet person, aren't either. So let's dive into some of this. There are three major theories as to the purpose of these web decorations: attracting prey, a warning to prevent damage to the web, and protection against predators. Let's take a brief look at the case for each. Since these web decorations would make the web more visible, one would think that perhaps they actually attract prey. And in fact, a number of studies dating back to 1990 found a correlation between web decoration and increased capture rates. Mystery solved, right? But then several studies found no prey attracting effect, and some studies even found that web decoration reduced prey capture rates. In 1998, Todd Blackledge did a study that took a less common approach to the problem. Instead of looking at how much prey the spiders captured when there was or wasn't a web decoration, he manipulated how much food the spiders were getting, then saw whether or not they built one. And he found that hungrier spiders, who you would expect to try harder to attract prey, built smaller stabilimenta and built them less often. Spiders that were allowed to pig out as much as they wanted actually increased the size and frequency of their web decorations. So could it be that web decorating doesn't lead to lots of food, but rather lots of food leads to web decorating? The plot thickens when we look at the nature of web decorations. In 2000, Marie Herberstein found that in Argiope kaiserlingi, which make these cruciate web decorations, webs that featured all 4 elements caught more prey than webs that had only 1 or 2. But again, those observations couldn't distinguish between whether more decoration means more prey, or more prey means more decoration. So there is evidence that the decorations attract prey, but it's kinda sketchy and we don't completely understand it. And it raises the question, if that's what the stabilimentum does, then why don't other daytime active orb weavers build them? Is prey attraction the purpose, or is that just a byproduct? We don't know. A second leading theory is that the spiders deliberately make their webs more visible so that birds won't fly into them and destroy them. Now this seems pretty reasonable, as the web itself is a pretty significant investment by the spider, and being knocked out of the web puts the spider on the ground or some other surface, where it's far more likely to be picked off by some other predator. A larger animal crashing through the web, then, is a significant danger to the spider, and it stands to reason that they would take measures to prevent it. This idea was put forward by Thomas Eisner and Stephen Nowicki in 1983. They actually tested it, using webs from spiders that made their webs at night, and didn't make web decorations. They'd wait until the spiders finished making their webs, which was at like 2 a.m., then took the spiders out. And after this middle-of-the-night eviction, they put artificial web decorations made of paper in 30 webs, and left 30 more alone. Then throughout the next day, they watched how long those webs all lasted. By noon, over 60% of the decorated webs were still intact, while only 8% of the undecorated webs remained. The rest had been completely destroyed, probably by birds flying through them. And they did once actually witness a bird fly right through an undecorated web, then disappear before they could interview it about the experience. As well as several times witnessing birds abruptly change direction just in time to avoid flying face first into a decorated web. This idea was further supported by a study of 4 islands in the Mariana Archipelago, one of which is Guam. Now the thing about Guam is that it had no snakes, until somebody's whoopsie-daisy accidentally introduced the brown tree snake in the 1940s. With no natural predators at all, the snakes had it made, and in the span of a few decades virtually wiped out all of the birds on the entire island, and to this day, Guam has virtually no birds, unlike the islands right next to it. Native to this chain of islands is Argiope apensa, and in 1993, Alexander Kerr studied their webs and found that on 3 of these islands, about half of these spiders' webs had stabilimenta, while on Guam, only 16% of the webs of this same species had them. So it could be argued that with no birds around to fly through the webs and wreck them, the spiders stopped bothering with this whole web decoration chore, while their relatives on the other bird-populated islands were doomed to continue with it. On the other hand, it could also be that with fewer birds, prey insects became more abundant, reducing the need for attraction lures, so it's still ambiguous. In 2011, Andre Walter and Mark Elger tried to test this further by abducting some St. Andrew's cross spiders, Argiope kaiserlingi, having them make webs in the lab, then damaging the webs on purpose to different degrees to see what the spiders did. The spiders whose webs were more heavily damaged went on to build bigger web decorations. To be a bigger warning to birds, right? Well, they also made smaller webs overall than the spiders whose webs weren't damaged. So it's possible, again, that the smaller web was the actual response to the damage, and the larger decoration was made to better attract prey to compensate for the smaller capture area. Ugh! A third major theory is that this web decoration protects the spider from predators, and it has been observed that spiders with web decorations have a higher survival rate. Possibly because the decoration makes the spider look bigger than it really is. It could also be related to this remarkable anti-predator behavior. Watch what this spider does in her web when I disturb her. It almost looks like this is just elastic motion, like I tapped her and the super springy web is just bouncing back and forth. But watch what happens when we slow it down to 1/20th speed. Watch her abdomen closely. Does this look at all familiar? This is absolutely deliberate and results in a very blurry picture for an attacker, confusing them and making it difficult to actually locate the spider in the web. In 2003, Daquin Lee and a team in Singapore went poking at some Argiope versicolor to check their responses and found that 53% of the adults with web decorations did this pumping thing when they were touched, but only 14% of those without decorations did. They were more likely to just shift or drop out of the web. So there seems to be a connection there, but no one has duplicated those results so far. And the particular reflective properties of the silk would make the spider visible to birds, but camouflaged to wasps. Again, this could go either way. With all of this conflicting evidence over the past 150 years, it might seem like we're running out of ideas. But there is one little bit of consistency that scientists have picked up on that might point us in a promising direction for future research. Most orb-weaving spiders build a retreat at the edge of the web. However, none of the spiders that build retreats build web decorations, and none of the spiders that build web decorations build retreats. So is the stabilimentum somehow performing the function of the retreat? Is there a link between the purpose of these two structures? The mutual exclusiveness suggests that one is replacing the other, and there's some evidence to support it. Spiders with heavy web damage build more decorations, they build less decorations when there's no birds, and those that build decorations tend to survive longer. But we need to investigate further to really explore that. And what is the link between web decoration and these wrap attack styles? As you can see, there is still a lot of unanswered questions about not only these spiders, but all web decorating spiders. They've been maddeningly slow to give up their secrets. In examining the webs, though, we might also ask, what's this great big ball on the edge? Here's Madison making one of these great big balls, and this, my friends, is an egg sac. Spiderlings normally emerge from the egg sacs in April or May, and the outer covering of this egg sac is made of a combination of large diameter fibers and small diameter fibers, and the spiderlings actually use digestive fluids to dissolve the small fibers while chewing a hole in the larger ones. Once one spiderling makes it out, the next one follows behind, enlarging the hole a bit if necessary, until all 400 to 1,000 spiderlings have left the building. Surprisingly, these spiders actually grow from spiderling to maturity over the course of a single year, with males maturing in late July to mid-August, and females maturing in August through October. This can vary a bit. Up here in Nova Scotia, Madison here molted to maturity as early as late July, so I think the northern ones might have a shorter season. It has been observed that the faster they grow, the shorter they live, as documented in 1972 by Charles Reed at Temple University in Philadelphia and Peter Witt from the North Carolina Department of Mental Health. The North Carolina Department of Mental Health was weirdly interested in spiders in the early 70s, it seems. Incidentally, Peter Witt was the same guy who did all those experiments giving psychedelic drugs to spiders to see what effect it had on their web building. The 70s were wild. Anyway, Come the fall, it's time for romance, and the females start letting their pheromones out into the air, calling suitors near and far. Cater Olive tested this out in 1982, creating large screen cages outdoors with plenty of female Argiope spiders in them, and sure enough, males started gathering on the downwind side of them. When males come across a female's web, they approach the edge of the capture spiral and begin a series of shudders and wags of the abdomen before slowly approaching the hub. If the female is receptive to all of this, she'll eventually expose her underside, and the male will insert a pedipalp. This is where things get a little weird. Males actually break off a piece of their pedipalp to plug the genital opening, preventing other males from mating with the same female. This is surprisingly common in spiders, actually, and is fittingly called a mating plug. Don't think too hard about it. What this means, though, is that for the male, each pedipalp is sort of a one-shot deal, giving them a choice. Try to mate twice with the same female, or try to survive the first mating and find a different female for the second. Now, observations have found that males tend to settle for any female they can find for the first mating, then get choosier for the second, assuming they survive long enough to attempt one. We're not actually sure what makes these spiders more or less attracted to each other, but they do seem to have some preferences. Females will routinely attack males, though, and this might actually be a matter of personality. In 2013, Matthias Fulmer and Kapil Kadka found that females that had a history of pouncing on prey more quickly were also more likely to attack males before or during mating. But really, females attack the males most of the time. Most of the time, the male also escapes. But if he achieves a second mating, he dies anyway, in something called programmed death. Within minutes, his heart just stops, whether the female attacks him or not. We don't really understand the mechanism or purpose of this, but I guess when you've got one-shot genitalia and you've already used both of them, why carry on? The females can then store this sperm for several months if they want to, before actually using it to fertilize eggs and make the egg sac. Then the females die in the late fall, leaving the spiderlings to overwinter in the egg sac, hatch in the spring, and start the whole cycle over again. That's what I've got for you for Argiope aurantia, the yellow garden spider. These can be sort of maddening, while at the same time that's part of their appeal. We have a lot more to learn about these spiders and others like them. Their beautiful web decorations have mystified scientists for nearly 2 centuries, and continue to do so, but perhaps this coming century will hold the answers for us. But until then, welcome these spiders to your backyard or garden when you see them. Their impressive size and striking coloration definitely capture our attention. If you're interested in a more detailed picture of how orb webs are made, check out the Spider Basics series, where I explore spider biology and ecology in a broader sense than just a single species. Don't forget to click like, subscribe, click the little bell so you get notified when I put up new videos. If you like this channel and want to support it, Patreon is the very best way to do it. The whole story of Madison driving me half crazy is told in more detail there, along with research notes, additional behind-the-scenes stuff, and other exclusive content. And of course, a huge thank you to my patrons who definitely keep this channel going. I deeply appreciate the support and couldn't keep going without it, so it counts for so much. You can also check out my Shopify store and pick up some channel merch. A lot of you asked for this on a t-shirt, and I finally added that. That also really helps me out and keeps me able to do these videos. And these are great gifts for going into the holiday season. We're going into winter, but I have some good stuff planned for the next couple of months, so stay tuned. You can also follow me over on Blue Sky. I'm giving that a shot. Maybe we'll see you there. Until then, thank you so much for watching. I hope you've learned something about this spider in your yard, and I hope to see you next time. Cheers.